Aryan, you done the quiz? Done the quiz? What you wrote? No, it's non-homogeneous.
Yeah, it's not homogeneous.
Right.
Same.
It's the same thing, but we call it non, right? I was.
Everyone is here, right? Nathan is also there. Oh, Niranjan.
Hey, Dr. Sajas, good morning.
Down? Oh, because you're remote. It doesn't reflect up. If you point there. It might reflect up. Might.
It used to work with the TV.
Yeah. Surface corrugations of the walls are smaller than the wavelengths of the acts like a mirror. I think that's how it's. How are things going? Any? I don't know. Due? No, not due, right? Was it due today actually before? No, right? It was due Monday to begin with, but I posted it very late. So I forgot. If students forget, then they lose points. If teacher forgets, nothing happens.
You should give us bonus points.
It should be like that. I would say that. I think that's blame it on the system. I think powerful people get away. Like in this classroom, I'm more powerful than you guys. I get away with it. You guys do the same thing. You guys penalized. So you guys want more points for that?
Yeah.
But then everyone will get the points, right? Okay, I'll do something about that. Remind me again. If I don't do it. I should also point out that there were a few students who came and asked me about the grades. All of you can get an A, so don't stop working. If you stop working, then I cannot help. Like that's the end of it. But I'm not saying if you work, you will get the grade, but then at least you qualify the minimum requirements. Right? So don't stop. So this is a graduate course. A lot of, I mean, that, again, teacher decides too many factors there, which is good or bad, however you say it. It's not as transparent as an undergraduate course. Like most of the times it's very transparent. If you do this, you get this. But here the transparency is less. For the whole class, I don't think, at least I tend to change things, but as a whole class, I think there's still room for an A. That's fine. Point. I typically, if you go ask me, I typically go for, if everyone is working hard, then I try to give an A. And if I feel that no, the hard work is not representative of something, then I try to be more careful. Yeah, it's hard for me too. It usually comes back on me saying that I'm reducing the standard of the assessment as a whole university. So that's the typical discussion that comes out. I try to be fair on that part also. That's the but it's not easy. Does that help? Well,
If you are getting an A.
I'm getting an A?
No, we are getting an A. Can you stop trying?
Can we assume?
Stop trying.
Who you mean to say that?
You're already getting A.
Yeah, that is surely one factor. If I tell you that you're getting an A, then you will stop trying. But that's not the only factor I'm trying to say. There will be see, somewhere, like you guys are answerable to me, somewhere as a whole, I don't think our department is good enough that they don't question me on what, or in our university as a whole, there are some rules, there are some laws that are made where faculty have a lot of independence. So no one questions me. But as a whole university, there is some standardization that we have to meet. And the question raised is that if you start giving A's to everyone, then what are you doing here? That how is that possible? So somewhere it might come out, and then I have to be answerable there. Does that make sense? I gave a vague. I still did not give you a precise answer, but those are the struggles we go through, and that is a very personal thing on the faculty. Like I might be more lenient compared to someone else who might be very rigid with the rules. So you guys are all TAs. You must be doing this. Right? Somewhere you grade, and it must be coming to your head that what's the basis of your grading? Like how rigid are you?
Everyone gets A in my lab, all semesters.
Like you can compare it with, so let's say you're like this sounds easy, give it an A, that sounds easy. Now let's say that you're on the Carbondale main road, and there is a rule that if you speed up, you get a fine. Now, how lenient are you? You should not be rigid, I agree, but every leniency leads to some mistake in the future. And those arguments can be brought here. Like you can say that my A can lead to something happening wrong 10 years later, and maybe my A contributed to that. Right. So this becomes a reasonable debate very quickly. So giving A's is not a solution. That's the way I would say. But we don't have to be all fails also is not a solution. I try in between. I don't know what exactly I do, but I try to be reasonable to myself. Yeah. Okay, that's the hard question. So let's do something simple.
What are the topics we are?
Going to cover Green's function. Okay, Green's function is a broad idea. As you have noticed, inhomogeneous differential equation is what is Green's function. And inhomogeneous differential equation can have different homogeneous parts. The simplest is when the solutions are exponentials. And that's what we are doing. Exponential functions are solutions to harmonic oscillator. Then we do this. The same thing happens if it was Bessel function or spherical harmonics or Laguerre functions. You can change the functions and everything can go through. And that's what I'm trying to bring out here. I'm spending a lot of time on exponential functions level. So the harmonic oscillator, I'm going to spend maybe 2 weeks, one more week at least. And those ideas, immediately I'll make a big leap and say that, oh, this is applicable for everything. And in principle, it is technically applicable, but I will not have time to cover all the special functions. Like maybe Bessel functions is what I will do. I have a choice of doing special Bessel functions or spherical harmonics. And Bessel functions is, at least the way I do it, is very standard. Like it's the way everyone else probably does it. Maybe I use integrals instead of series expansions. But the spherical harmonics that I do is not very common. It's a very few set of people who do it. So I sometimes think that I will teach more if I do spherical harmonics. But that's a decision I have to take in the next couple of weeks. Is that the question you were asking? Did I answer? Yeah. So that's the different functions, and especially spherical legendary polymorphisms, which are based on spherical harmonics. Okay. Anything else? Any comments? Oh, I had a comment. Digression again. 15 minutes already. Thanksgiving break. How many of you are going to be here in the town? Just curious. You're not going to do that.
I may go.
You may go. Okay. Half of it, yeah. So I was thinking, like some of the students, we'll just go to a park and have a lunch or something. We will. It's not a course requirement, not a course requirement, so it's just a friendly thing. So if you're not available, you're not available. No course discussions will be entertained. In a sense, you don't miss out on.
No, it's going to Giant City Park.
I think so. I usually like that. I'm going to the Giant City Park and like typically Dustin is the guide for us. But he may not be there. It's Thanksgiving. I'm pretty sure he will be coming home. He may not be there, but not really on Thanksgiving Day. Maybe Tuesday. Again, that's a thought I'm having.
The last time I went there was really cold.
Who what? Oh yeah, last time some of us were there. It was extreme. We chose the wrong time, but it was memorable in a sense. The extreme cold makes it memorable. Okay, yeah.
You mean Tuesday, the November 21st?
Yes, the Thanksgiving, right? You have a calendar. You have to look into the calendar to look at your Thanksgiving plan.
I'm looking for the dates.
Okay.
The whole week is off.
Yes. Okay. Yeah, it starts on Saturday 18 and all the way to 26th, the Sunday. It's about 9 days. Holidays. Yeah. We did not have a fall break. So about before 5 years, it used to be a fall break in October, and Thanksgiving used to be just one Thursday and Friday. There was 2 days Thanksgiving, and fall break used to be 1 week. So now the fall break is gone. Actually, fall break was not for 1 week. I think there also it was 2 days. So you combine them. So that's what happens. Was there anyone here? No. Okay, let's see. Okay, you have a homework 10. It is due still on Monday. I think you guys can, but anyway, there is some freedom there, right? These days. Homework due dates are just guidelines. This is after Thanksgiving, the Monday after Thanksgiving. Finally. The last day of exam week. And check on the dates also. Sometimes I make mistakes. You have to look into the calendar and check. So. Okay. We are doing Green's function. Green's function is a technique used to solve inhomogeneous differential equation. And what we are, the example we are covering is post-harmonic oscillator. But this is just an example, particular example. We are saying we started using non-homogeneous, not inhomogeneous, non-homogeneous. Did anyone check out whether that's all homogeneous or non or in both are okay? I see. Yeah. Differential equation. So what do the mathematics textbooks use? That also is both? I'll try to find out. Wasn't that a quiz? Yeah, that is a quiz. Oh, that is a quiz. So you guys have submissions. Okay. Yeah, I'll look into it. Yeah. So what do I mean by that? So I wrote this differential equation down. This is representing a harmonic oscillator with mass equal to 1 if you want, and the forcing is that was small a or big A. Let's use last time I used small a. Sorry for the switch. And here that it's not really necessary once I write that down. Omega naught square is, if you think of it in terms of spring, this is what it is. A of T is minus force over the mass. But once I have defined this, I really don't need that. So these are the parameters in there. But I do know need initial conditions, and I need x of 0 and v of 0, right? And let's say this is x naught, that's v naught, and usually when it is a not forced, I need to give x naught and v naught at least, otherwise nothing happens. But now that there is a forcing, I can put initial conditions as 0, so that's a convenient we can have. But that's your differential equation. Non-homogeneous means there's a of t in there. So immediately there are two things that comes out. So this is the homogeneous differential equation. And usually you say this is x naught of t. And that has solutions. X naught of t. These are exponentials. I omega naught t plus beta I omega naught t. So always a homogeneous differential equation will have, presuming it is second order differential equation, they will have two independent solutions. In this example, the two independent solutions are exponentials. Later, we will make a big leap when we say that there is another, for example, this will be Bessel function. There will be a Bessel function on the first time, Bessel function on the second time. Spherical harmonic, same thing. Always the special functions will come in two kinds, two independent functions, and they will form the solution to the independent or the homogeneous differential equation. If you want the inhomogeneous, what you do is you construct a new third differential equation. You say that's the Green's function. E, t prime, and this time it has a source only at t prime. So notice time, if you were to think of time as a linear straight line, so that's your time. T prime is a special time in that sequence of events that is happening. That's a special time t prime. So we are saying that this source on the right side is non-zero only at one time, which is t equal to t prime. Everywhere else it is 0. So it is almost this. It's almost the homogeneous differential equation, except at one point. And we will exploit that information that for t less than t prime it is this, t greater than t prime it is this, and at equal to t prime something is happening. So we'll do this patching. We will patch the two solutions at that interface, which is t equal to t prime. That will be our idea. So this is inhomogeneous, homogeneous, and that's the Green's function. And in the last lecture, we said, in an elaborate way, we pointed out that the solution in general, so irrespective of what happened in the last lecture, that those are all proofs and convincing you that this was true. But the solution is alpha times e raised to I omega t plus beta times e raised to minus I omega naught t. So that's your homogeneous differential equation. Remember last time we said any solution to non-homogeneous differential equation is a homogeneous solution which controls your boundary plus a particular solution, and the particular solution is the following. If I'm in general, you can say that. A of t prime. And still it is not completely solved because alpha and beta are to be fixed using initial conditions. This can change, as we will see today, this can come in different forms. Like some of this can be put into this, some of this can be put into this. So it's not unique. This Green's function does not come out to be unique. So that will be the arbitrariness, but all the non-uniqueness can be absorbed into this solution. Okay, so today we want to solve this differential equation, and that's what we will do. And once we have the solution, we will just put this in here, and then we have the major solution. But notice, I'm not going to, so when I wrote this down, plus no conditions, right? No initial conditions. There's nothing wrong in using initial conditions. If you use the initial conditions, that's perfectly okay. It will only change your alpha and beta. But I'm going to make it really clarify that you don't really need any initial conditions here, and still you can go through this problem. Okay, so that's our goal. So let's switch. Oh, I wanted to write bigger today. It's clearly not readable. Can you zoom in? Yeah, let's try to keep zoomed in. Because I looked at the videos and it's really not. I don't know how you guys manage. Do you guys look in the videos? Probably not. Okay. Okay. So we want to do this. So I'll take a small digression just to emphasize on this delta function, but it's very relevant. So comment, right? Few comments. Comments. Okay. Let's have a step function. And let's say this is t. This is equal to 1. If t is greater than 0, this is equal to 0. If t is less than 0. And this looks like, if I were to plot this looks like this. So this is 0. What is its derivative? Theta of t is equal to, this is 1 everywhere. So if I take it to be, I take its derivative, so it is 0. This is 0 everywhere. So that's 0. T less than 0, t greater than 0. And does that mean it is 0 everywhere? No. You say that this is 0, that's 0, but right at this point, it seems to be a delta peak, right? So we will use the fact that this actually is a delta function. That's a statement we are going to use. We can make this more precise now that we have studied complex analysis. We can define step. We did this. Direct step function was pretty much expressed in terms of contour integral. So you can make this more precise if you really don't like this simple intuitive picture. But step function derivative will be delta function. That's what you want to keep in mind. Is there any comment or confusion or clarification you need on that? Okay. Shouldn't be satisfying, but I'm saying if we are going to use that, and if necessary, we'll go to complex analysis. Okay. So that's your step one. The same thing, you can change this t minus t prime, right? So then we do d by dt is equal to delta function of t minus t prime. Notice there is a delta function on the right side of the Green's function. That means that whatever this is, one way of generating this is a step function. And what is a step function? That's a discontinuity at a point in the solution. If there is a discontinuity, it leads to a delta function. For example, I can have f of t could be equal to f1 of t for t less than 0, and f2 of t for t greater than 0. And let's also say f1 of 0 plus delta, that means slightly to the right, that's equal to 1, and f2 of 0 minus delta, that's equal to 0. What that means is that I started with a step function here, right? So that's 0. So this function is 0 here, except this could be having a form here, and this is 1, And that could be having a functional form here. So this is f of 1, t, f of 2. Of t. What I've captured here is that the discontinuity is exactly the same as step function. Otherwise, it is having a functional form there. So this can then you will have derivative of f of t will have a step function, delta function t of, so maybe the way to say it is so we would say f of t can be written as theta of t times f1 f2 of t. If t is greater than 0, it's this solution plus theta of minus t is f of 1t. This is a way of writing the above solution. When t is greater than 0, this survives. And I have the solution f of f2 of t. And when t is
Other way. Minus.
t is greater than 0, it's f2, right? Like t greater than 0, 1.
Here's that, 1 is greater than 0.
Oh, I showed this wrong. This is f2. Oh, that's what it said. That's f2, that's f1. Thank you. Yeah. Or maybe that's has to be changed now.
Dr. Sajis, thanks.
Fine. Okay. And the minus t makes sure that it is on the opposite side. So whenever there is a discontinuous function, step functions can be used to write that in an analytic form, in a closed form, if you want, instead of this. This is just a way of writing the same information. But now I can do derivative, right? So derivative of f of t will be equal to, now do just your standard distribution of derivative. When I hit this, there is a delta function. So that's f of 2t. But I can also hit f. So this is theta of t times derivative of f of 2 plus when I take the derivative of the step function, that's minus. So that's minus of a delta function. Delta function of a minus t is the same as plus t. That's 1 of t and plus derivative of f1. So that's equal to delta function of f2 minus f1 plus step function f2 over t plus step function of minus t times f1 over t. Okay. Now, I want you to put this together. There is a Green's function. Let me write this again just so that it's on the board. So there is a second derivative of a Green's function as a plus omega naught squared. As a delta function. Right. The first derivative of step function, and by step function I mean any discontinuous function, any function that is having a discontinuity will contribute to a delta function. Right. That means to say that the derivative of the Green's function must be discontinuous. At least that's a possibility, that's a possible way of building. Okay, so that's going to be a conceptual understanding we want to have. If the first derivative has a discontinuity, has a like finite discontinuity, that means the function itself could be continuous. So keep this in mind. For example, a classic example is magnitude of z. How does this look like? If I were to plot it, z magnitude of z, how does it look like? It's like a V, right? It's linear on the right side, linear on the left side, but it's positive on both sides, right? That's the magnitude of z. What's the derivative of this function? Derivative of the magnitude of z, it's 1 everywhere here, right? The slope of z is 1. Slope of here is -1. And there is a discontinuity that I have developed. And what will be its derivative? Delta function, right? So if I want to get a delta function on the right side, the Green's function should be of this kind, probably. Okay, we will show this more explicitly at this point, but I'm giving you a visual feel for that, is that it should be continuous, but its derivative probably should not be continuous. Because it's the discontinuity in the derivative, when you hit it, it gives you the delta function. If the function itself is discontinuous, then you will get a derivative of a delta function. If this is discontinuous, by here, you're having a delta function and a derivative of a delta function, then it will be a derivative of a delta function on the right side. You don't want that either. So you don't want to overdo things either. So if there is a fine balance of so-called delta functions, which is sensitive, right? So we want to be careful. So with that in mind, so let's proceed. Okay, so I'm going to go up. Oh. So let's go back to our Green's function, and we can immediately say second derivative squared plus omega naught squared times x of t, no, g of t, right? Green's function. Is equal to 0 if t was less than t prime, and it's also 0 when t is greater than t prime. Right? That has to be true because delta function survives at only one point. Again, remember, that's your t, and that's your t prime. T prime is a special point, and all the differential equation is written in the parameter t, but t prime is a special point in that variable line. If that is the case, these are homogeneous differential equations. I know the solution here. Right, so that's A times exponential I omega naught t plus B times exponential minus I omega naught t for t less than t prime. But the only catch now is that for t greater than t prime, it doesn't have to be the same solution. That is a different solution. There is no guarantee that it should be the same. No one says that. There is no requirement that. So these are homogeneous differential equations. We know how to work with them, but now we have 4 constants. Like remember, initial conditions has only 2 things we can work with. We have 4 constants we have to work with, and at t equal to t prime, what happens? So the immediate question you ask is, there is a solution here, and the initial conditions will give you 2 more conditions somewhere at t equal to 0. There is a solution on the right side, but what matches them? At t prime was an arbitrary point. What is the matching condition there? And those are called continuity conditions. So we want to look for continuity conditions. Continuity conditions at t equal to t prime. So the philosophy would be find a solution on the left, find a solution on the right, and right at the boundary, at the interface of t equal to t prime, we will have some conditions, but who dictates that conditions? And the point is that the differential equation itself dictates it. Differential equation has the information about this continuity condition. You cannot put in anything from outside. If you put it from outside, then it's no more, then there is some arbitrariness in that. So we have to derive everything from the differential equation. So let's go back to our Green's function and integrate it. So if I have a Green's function, I can integrate with respect to dt, the second derivative dt square plus omega naught square times g of t comma t prime, and do this integration on both sides. But when I'm doing an integral, I have the liberty to do the integral from whichever limits to whichever limits, right? So that's my line, that's my t prime. That's your t. And this I'm going to say is t prime minus delta, where delta is some very tiny number greater than 0, a small infinitely tiny number, and this point is t prime plus delta. Is that readable? Why do people write so small? Right, bigger. T prime minus delta, t prime plus delta, that's t prime. Is that better? Oh,
Yeah, it is readable.
okay. So this integral is going from t equal to t prime minus delta, t equal to t prime plus delta, t equal to t prime minus delta, t equal to t prime plus delta. Notice I'm deriving the continuity condition. Okay. If I do this, this is a total derivative. D by dt, derivative and dt in front, so that will contribute only at the boundary. So let me actually write this in 2 steps. T equal to t prime minus delta, t prime plus delta, dt, d by dt, notice total derivative, right? And d by dt of g of t comma t prime minus omega naught square dt t prime minus delta t prime plus delta, same thing, p equal to this g of t comma t prime. On the right side, as far as t equal to t prime is within the integration limits, delta function contributes. And I made sure that t prime is within that integration limits. T prime is in between these 2 points. As far as that is in between these 2 points, delta function will contribute, and that means that's 1. Okay, so and this is a total derivative, so this contributes only at the boundary, right? Total derivative means one way to do this is that this cancels out, and this is a total derivative, so it's just a function itself minus move the camera.
Please. Thank you.
Thanks. So, okay. This is d by dt of g of prime and t equal to g prime minus delta, t equal to g prime plus delta. And now I have this also in here. Now let me write this down. Okay, so this is yeah, so okay, let me argue this for a minute. T prime minus delta, t prime plus delta, dt g is equal to 1. Yeah. Notice I just now said that g, if the possibility is that g is continuous, so if g, if g was discontinuous. Discontinuous. So, within that point, that means the plot of T as a function, the G here, will be like this. If that is the case, that would imply that second derivative of G would be a derivative of a delta function. Correct? Is that clear, my argument there? If, like earlier I discussed the step functions, if there was a discontinuity in G, then there will be a discontinuity and there will be a delta function, which is not the case. We don't have derivatives of delta function. So that's not possible. Even if it was, what is the integration of this function? Even if this was discontinuous, what's the integration of this function from t prime minus delta to t prime plus delta? So that's this area. Right? That's the area under this function if I'm going from t prime minus delta to t prime plus delta. That's this integral. What's the area of this strip in the limit delta tends to 0? It is 0 unless this was infinite, unless there was a delta function there. But if G had a delta function, then its derivative will be worse, and that will contribute to the second derivative. But we don't have such a thing. So the only possibility is that this is continuous. Okay, so this has to be 0. This can be done more concretely, but that will really just take be a distraction, and it will take 15 minutes to do it algebraically. But geometrically, it is hopefully very convincing. But there are analytical proof or algebraic proof for that. You can start with the differential equation again, do the same thing, do the integration there, and you can do it. If that is the case, we immediately know that this is equal to 1. And I also made the argument that if there was a discontinuity, then there will be a first derivative. So we also argue plus, right? Plus the Green's function itself, discontinuity, t equal to t prime minus delta, t equal to t prime plus delta should be equal to 0. That means it is continuous. So these are the two conditions. So if I go back and write down my continuity conditions, so it's right here, continuity conditions. Oh, you want to? Yeah. Oh, you're not able to focus. Yeah. Like this is what happens because I do this hot porridge seminar. So I have to take care of the camera, and there are 3 people attending from outside the town. Whenever I'm concentrating on the lecture, I'm forgetting the camera, and it's impossible to concentrate on the lecture if we are concentrating on the camera. I think the best is to look at the camera and work. I think. Okay. But yeah, sorry. Yeah. Okay, let's try. Okay. So, summary of this is that notice this was derived. This was, I didn't impose this. These conditions has to come out from the differential equation, otherwise it's arbitrary. So the continuity conditions are that the Green's function at t prime plus delta and t prime, right? This was t, remember, right? This is t. T evaluated at this point. Remember again, this is t, and that's a special point t prime, and this is t prime minus delta. T prime minus delta, t prime plus delta. And the difference between these two, t of t prime minus delta t prime, is equal to 0. Is that clear what I'm writing? This is t actually t evaluated at t prime. And the second condition is that the derivative of the Green's function. T comma T prime evaluated at T equal to T prime plus delta minus the. And you do this in different quantum mechanics a lot, right? But there we are talking about wave function that is meaning to those derivatives. This is abstract, like green function out of the blue, right? It is not the actual physical content. This is T equal to T prime minus delta is equal to -1. It's not continuous. Derivatives are not continuous. It is -1. And did I lose any dimension by any chance? One, hopefully not. So this also tells that the Green's function should have a dimension of 9, right? Because right side is 1.
Is it the same as Dirichlet normal condition?
Yes. Yeah. Okay. No. In the following sense, yes, in the sense that Dirichlet condition is on a boundary, right? Typically on a physical boundary. Like there you define a problem saying that there is a conductor and on the boundary it satisfies 0. Like here, this is not really a boundary, right? T prime is some arbitrary point I pick, which I'm going to use to build the whole function. So it's in that sense, it's not. So in the strict sense, it is continuity conditions. Dirichlet conditions are on the boundary. Like here, I have put initial conditions. That will be like that's one of your homework problem for next week. Is that we will have 2 conducting plates and there will be a charge in between. And my potential will have to satisfy Dirichlet condition. That means it has to be 0 on the boundary. Right? Those are Dirichlet condition. And then you don't write the derivative. Instead, you say this is 0 on the left, this is 0 on the right. So I have provided condition. You can also have the derivative going to 0 on the left and right, and the other. Okay. So typically, you don't use Dirichlet condition at the continuity level. So this is a patching condition. So our problem boils down to half an hour remaining. So the question then is I have my Green's function I have to solve for is T minus T prime A times exponential I omega T plus writing this again. I earlier wrote this and C e raised to I omega naught T plus B e raised to minus I omega naught T for T less than T prime and T greater than T prime. These are 2 conditions for unknowns. Right. So I will be able to solve for only 2 of them. Number of equations can solve only for that many unknowns. So I will be there will be 2 unknowns remaining. But whatever that will be, that will get absorbed into the homogeneous differential equation. That's going to be our key. So 2 of them solve it using continuity conditions. Remaining 2 get absorbed into the alpha and beta, and the initial conditions will fix it. So that's our goal. So let's very quickly do this. From this point on, you roughly know what it is done. So let's do the derivative also. So get the derivative also once. This is u of T comma T prime. That's equal to I omega naught times I A times e raised to I omega T minus I omega naught D. That should be the easy part. I omega naught C minus I omega naught D. This is T less than T prime. T prime plus than T. So now I have the derivatives, I have the G. I have to patch this up using this conditions. So let me do that. Any questions at this stage as far as the strategy goes? Okay. So get the capsule buffer, right? So it is P greater than plus delta has to be subtracted from minus delta. That means the bottom solution has to be subtracted from the top one and evaluated at P prime. So it is a plus delta, but there is nothing funky, funny happening at beyond P prime. So we are good at just substituting P prime. So this is equal to C times exponential I omega naught P prime plus B exponential minus I omega naught P prime. So that's your minus of A times I'm supposed to write T prime plus delta, T prime minus delta in those points, but I'm taking the limit delta tends to 0 at that state. There is nothing funny happen. So that's equal to 0. And the other one is I omega naught exponential of I omega naught T prime minus I omega naught. Nope, what is missing? C. Is equal to minus 1. So this can be written as C minus A, right? So C minus A times exponential I omega naught prime, C minus A and B minus B, right? So B minus B times exponential of minus omega naught prime, that's equal to 0. And this one, let me do something. I can write an I omega naught on the right side. It is minus 1 over I omega naught. And this one is C minus A again, C minus A. And minus of B minus B. Just change it up a little. That's easy to do. How do we work on this? So C minus A then equal to C minus A is equal to the determinant, right? So let me write the denominator first. So this is exponential I omega naught prime, exponential I omega naught P prime, exponential minus I omega naught P prime, and minus of exponential and the determinant. And the numerator is you put this instead of this, right? So it's 0. Minus 1 over 5 e raised to what? If you want to move the camera. Denominator has simple exponential times exponential, that's in the opposite sign, that's the inverse of each other. That's minus 1 and a minus 1, minus 2. Denominator and numerator 0 times this is John, and this is plus, right? Plus 1 over I omega naught times e raised to prime. That's equal to minus 1 over 2 I omega naught. Solve for C and A. Same thing we can do for D and B. D minus B. That's equal to, now I have to replace the right column, right? So I'd say this is exponential of I omega naught t prime. This is a familiar technique, right? To solve linear differential equations? Yes, no, no one is smooth. Oh, no. Okay, no. Digression. Just a statement, how about that? A times X plus B times Y is equal to, let's say, alpha. And C times X plus D times Y is equal to beta. Okay, that's two linear differential equations. All of us have at least one method of doing this, right? You would say multiply, make the coefficients the same, or solve for X, substitute in the first equation. That is all fine, but here is a prescription if you want. In general, it will always work out like this. This is the determinant of, in the denominator, you write the coefficient. So this A, B, C, D. Okay. In the numerator, if I'm solving for X, I have to replace my A and C with alpha and beta. It is alpha, beta, B, D. The determinant of this. Determinant is familiar, right? So it is alpha D minus beta B. Always works. It's an easy thing to use. But often I notice that sometimes I try to teach this in 200 level plus, and this comes out to be harder than the way you do it. So they don't really appreciate that. But I kind of typically use it. It's just easy. So especially in these problems, I think that is the symmetry and minus 2 comes up. Or I always feel that there's always a symmetry. And C, Y will be equal to, just for your information, AC alpha beta divided by A B. Just that. Yeah, nothing special about it. Okay. That's it. That is all I can tell you about that. You can derive it if you want. Quiz. Derive it. Right. It'll always come out that it's not a optional quiz. How about that? Okay, so you don't have to. Okay, so let's do this. This is exponential I omega t. Again, e raised to I omega naught t prime. And now you replace 0 and minus over I omega naught. And the denominator will be the same, so I don't have to write it again, so that's minus 2. That's equal to minus, plus this time, plus 2I omega naught times exponential of I omega naught t. So, move the okay. So I have to go back and write the solution now for the Green's function. Where should I write that? Go back upstairs. Use that so I can. Okay, let's get the solution done. So I have D and B, so I can write my solution, right? So G, a function of t comma t prime. Remember, I have only solved for 2, right? Only 2 solutions has been done. So this remaining, I have to keep it as it is. So one of the ways to do this is that keep A. So this is the arbitrariness that starts coming in. Which 2 coefficients I keep and which 2 coefficients I do not keep. There are infinite ways of doing that. I keep half of A, half of B, half of C. So one of the simplest is that I keep the top one intact, solve for C and D. And that is going to be the variation. Different, you will hear about retarded Green's function, advanced Green's function, Feynman Green's function, Wheeler-Green function. There are different names associated with these. That is all based on what you solve for. Right? So that's all has interesting physical features in there. But for our purposes, it's just random. So this is, we will keep it as it is. B minus I omega naught t. So this I don't touch. T less than t prime, and for t greater than t prime, now C, right? C is equal to A plus something, so it is A A minus 1/2 I omega naught times exponential of minus omega naught t prime times e raised to I omega naught t, and plus b, which is p plus 2I omega naught times e raised to I omega naught prime and e raised to minus I omega naught t. This is for t prime less than t. Readable? Readable. Okay. The second part, you notice that A and B terms are there on both sides. Right. And the added terms that do not have any coefficients, that's there only on the second side. Which means I can use step function to define this. So I'm going to write this, the notice. A and B are there already, that's your homogeneous part. Not very interesting. The rest of it is equal to, or let me say, write this to the beginning as 0. On the top, on the right, on the bottom, what is it? Let me write that in 2 ways. So, e minus e prime. E minus e prime. So there's minus 1/2I omega naught exponential of I omega naught t minus t prime. And the next term is minus of exponential of minus I omega naught t minus t prime. With t less than t prime less than t. With me? Is that clear? That is a sine function, so let me capture that. A exponential I omega naught t plus b exponential minus I omega naught t plus 0 on the top. The bottom sine is exponential of x minus of exponential of I minus x times 2i, right? So this is minus 1/omega naught times sine function of omega naught times t minus t prime. On simplicity. Okay. That's a step function. So it can be written as a exponential I omega naught t plus b exponential minus I omega naught t. Write this as a step function. So this is plus, like it's minus 1/omega naught and step function t minus t prime times sine of omega naught t minus t prime. That's your Green's function. And Green's function is always off by a candle. Green's function is always off by a homogeneous solution. This does not give you the delta function, right? This is just 0. So this is the homogeneous solution. And that with the negative sign is a particular solution. This is the important one. As I said, I've been repeating it again and again. That the homogeneous solution has a lot of arbitrariness, one from many places. This is not relevant. This is the term that will give you the delta function on the right side. And it's clear that step function, when you take the derivative, that's what will give you the delta. So let's drop this. And this is called by the way, this way of writing, as I said, there are many ways of collecting it. This is called the retarded Green function. So let's just give it a name, g of r, t power t prime. That's equal to minus 1 over omega naught. Hammer like this. Minus t prime times phi. Now, does this really satisfy the differential equation? Let's do that. If that is really the solution, if I put this on the left side, I should get the right side, right? I should get the delta function. So let's take the derivative. D by dt of g of r is equal. It hits two places. So 1 minus 1 over omega naught delta function minus t prime times sine of omega naught t minus t prime plus or minus omega naught minus t prime, and omega naught goes away. When I take the derivative, it becomes cosine. I also need a second derivative. So second derivative of Green's function of t r is equal to minus times derivative of delta function, and this is sine. Remember, at t minus t prime, that's equal to 0. So there's more terms in here. Actually, I could do it here itself, but that's so minus of again a cosine. So that's your sine is cosine, so it's minus of delta of t minus t prime times cosine of omega of t minus. All right. Take the derivative here. Again, I get a delta function t minus t prime cosine of omega naught minus t prime, and take the derivative, so it's minus omega naught, no, plus this time because cosine of the minus t prime times sine of omega t minus e. This is the Green's function itself, right? This is g of r except for a minus sign. So this is equal to minus 1 over omega naught derivative dt delta t minus t prime prime, and that is two delta functions here. Know what needed. When t is equal to t prime, cosine of a function is cosine of 0 is 1, so I don't need to keep the cosine, so I just keep the delta function there. And this is minus 1 over omega naught times g of r. Oh, my we have to put down. Zoom out. Okay. Write this. Oh no, that when I write this as omega naught, I need an omega naught square. Omega naught square. So I have second derivative equals square plus omega naught square. Oh, I think I wrote this wrong, right? So I'm writing, I absorb an omega naught here, so this is omega naught square. I want to. It's okay, so plus omega naught square times G of R is equal to minus, so let me put a minus sign also. So that's equal to 2 times delta function of T minus T prime. And write this as multiply a T minus T prime, T minus T prime times d by dt of delta function of T minus T prime times sine omega naught T minus T prime over omega naught T minus T prime. That's equal to 1. That's equal to 1 in the when you're having T equal to T prime, that limiting condition is 1. So apparently, the way I have written it, you really do not get the delta function. That seems to be 2 times the delta function times a derivative of a delta function. But it turns out that this is also a delta function. So let's show that in a minute. I have 5 minutes. Okay. Go here. No, that's it. So let's have E1, let's say delta function of T minus T prime. This is a new function I'm defining. That's equal to that's equal to T minus T prime times derivative of a delta function. Do an integration by parts. So this is equal to say inside an integral. So let's say dt delta of T minus T prime. That's say T1 minus infinity plus infinity is good. No, let's keep it from finite, just to make sure that no arbitrariness. So it's T1 to T2, that's equal to integral of T1 to T2. Integrate by parts, we say d by dt, T minus T prime times a delta function, plus, no, minus of when I hit on the derivative itself, I get a delta function. This term is 0 on the boundary. At T1, delta function goes to 0. At T2, delta function goes to 0. We are saying it is around the points T1 and T2. This whole thing is equal to 0. So the way you can, what happened to the minus sign? Did I miss the minus sign here, right? Oh yeah, I did, right? When I go from this to that side, this minus sign should become, so minus became a plus, this should become a plus. So the previous line, so here this should be a plus sign in the derivative equation. Yeah. So What that means is that, so delta function, so basically what it means is that t minus t prime times the derivative of a delta function is practically is equal practically, right? So this is the same as a minus of a delta function. For all purposes of our calculation, that's a minus of the delta function, and then you immediately get that this satisfies. Or is equal to 2 times delta function, t minus t prime, and then the minus of delta function, t minus t prime, that's equal. Which is true. But notice how fine the arguments are. Like all these delta functions are practically divergences. They are ways of absorbing divergences at a point, and we are having very fine cancellations there. It was necessary to get that factor of 2 out, so that should give you a feel for that. But having the Green's function, now we can go back and get the solution, and we will do that next time. Okay. So, and your homework, most of your homework is there in today's lecture. If you go at various pieces of the lecture, the homework you should be able to do just. But be careful, be critical about the homework, ask every step, why am I doing that? So that's the important part of it. Okay, thank you.
Thank you so much, Dr. Sajesh.
No, thank you, Ranjan. Yeah. I try to. Yeah.
Any volunteer for the?
I can do it. I think I have done this before, I think, but now it's. Yeah, I know. I experienced this in potpourri, so I completely understand your situation. Every time I focus, the camera is off for minutes and. But I have, since during COVID, I do this, and at that time I was alone. So I have a feel for the camera, and then I keep changing it. It's not very fair. I can do it. It's you're working for everyone. You want to make sure that no one else needs a particular that nice. I can imagine if I was in this class, I will boycott all your other almost. If